to put together a few videos that are just going to involve looking at certain integrals and trying to decide how to approach them. We want to do the antiderivative of this function, and what we would want to think if we don't really know how to approach a certain antiderivative is hopefully an antiderivative formula is going to work. And because we have this product here, that's a little bit of an issue. So the next thing you might think is, well, is there any algebra that I can do to basically get rid of the product? And there's not really any in this case. You're not going to be able to rewrite this as anything but e to this power times sine of 2 theta. It is a product. So it doesn't seem like a u substitution would work here because we can't really let u equal one of these inner functions. We're not going to get the right cancellation to occur. So since this is a product, it seems like what might work is integration by parts. And the formula that you would use for integration by parts is you're starting with an integral that's u times dv. We're going to have to assign u, we're going to have to assign dv, and then what we're going to do is we're going to produce du, we're going to produce v, and then we're going to have to construct this other side. This formula is just derived with the product rule for derivatives, and it says the integral of u dv is going to be equal to uv minus the integral of v du. So we're starting with what's on the left side of this formula. Our job is to assign u, assign dv, produce v, produce du, and then try to construct this right hand side of the equation. So I'm going to let u equal something, I'm going to let dv equal something. Whatever I put in for dv has to also include the d theta, the differential here. There's a little acronym that I like to use that can help you decide what you should let u equal, and this works in most instances. In this case, it's not really crucial that we make u a certain thing and dv another thing, only because of the nature of this particular integral. But this would represent inverse trig functions, logarithmic functions, algebraic functions or polynomials, trigonometric functions, exponential functions. We have a trigonometric piece and an exponential piece, right? Trigonometric piece, exponential piece. The further something is to the front of this acronym, so the t is above the e is in front of the e in this acronym, the more likely that's to be set equal to u. So I'm just going to go ahead and let u equal sine of 2 theta. I'm going to let dv equal e to the 3 theta. And then the d theta is part of dv. And so what we want to do is we want to compute a du, right? We see a du here. We also want to compute a v because we see v in 2 places over here. So to compute a du, we're just going to do the derivative of u with respect to the variable theta. And when we do that derivative, it's just a little chain rule. So the derivative of sine is cosine. Inner function stays inside of that, and then we multiply by the derivative of the inner function. So what does du equal? Well, du is going to end up equaling cosine of 2 theta times 2. So I'm just going to put a little coefficient out in front, and then I'm going to multiply by d theta, right? I'm basically solving that equation for du. On the other side here, I need to produce a v. And to produce a v, I'm going to have to integrate each side. So when I integrate each side, the integral of 1 with respect to v is v. And then the integral over here, it's actually going to require a little u substitution. A little substitution letting u, or since I already have a u here, if you're actually going to write this stuff out, you might want to let a different variable, w, equal that exponent. Think about what dw d theta is going to be. It's going to be 3, right? The derivative of this is going to be 3. That will pick up a constant of 1/3 for us when we actually do the integral. And I'm just going to kind of bypass writing out the substitution steps, only because this is going to get a little bit lengthy. I want to make sure we can do this all from start to finish here. So we've produced a du, we've produced a v. I did this integral with a little substitution. I'm not going to put the plus c here. I'm going to wait till the very end of this, and whenever I have the antiderivative of this written at the bottom of the screen, that's when I'm going to tack on my plus c. So I started with an expression that I claimed was equivalent to this. I assigned u, I assigned dv. We've now produced du and v, so now we can construct what we have over here. So the original integral is equal to u times v. So u times v, I'm going to write that as 1/3 sine of 2 theta e to the 3 theta, and then minus the integral of v. Now we have this 1/3 here. I'm going to pull that 1/3 out in front of the integral, right? You're always allowed to take that constant out in front of the integral symbol. And then I'm going to have the conclusion of v go inside of it. Can't factor that out because that involves the variable theta. And then I'm going to have du beside that. Now if you notice, du has another constant attached to it. It's a 2. I'm going to factor that constant out as well, and I'm just going to kind of put it in this numerator. So I have minus 2/3 the integral of e to the 3 theta, and then the rest of du is going to be cosine of 2 theta d theta. Now what you notice happening here is you notice that you have another integral here that you can't quite handle. When you use integration by parts, its purpose is to produce an integral at the end of this line, an integral right here that you can actually evaluate. This is very similar to what we started with. When you have products of exponentials and sine or cosine, what I refer to that type of integral as is a cyclic integral, because if you apply integration by parts enough times, you will cycle back to the original integral and you'll be able to solve for that. So this is a pretty special circumstance. We're going to apply integration by parts again. I'm going to go ahead and take a break from the video here just to kind of bypass all this work, but I'm going to do another round of this, and once I get all that in place, we'll pick things up from there. Okay, so what I did was I basically applied another application of integration by parts to this integral that's sitting right here. So I let u equal cosine of 2 theta, the piece that's here. I let dv equal e to the 3 theta, and then the d theta goes with that. I did the derivative, little chain rule. I solved for du. Over on the other side, I did the integral to produce v. That was going to require another little substitution. It's the same integral that we did back here in the first application of integration by parts, actually, so we get v equal to 1/3 e to the 3 theta again. I'm still working off of this line. I'm going to copy this down. I'm not changing this piece at all. I'm just bringing that straight down. I'm not changing the minus 2/3 at all. I'm bringing that straight down. I'm replacing this integral with another application of integration by parts. Now, integration by parts involves 2 terms, so I'm going to have to make sure I use a set of grouping symbols here because I need this minus 2/3 to be able to be distributed into everything from that second application of integration by parts. So when I apply integration by parts a second time, now my formula is kind of up off the top of the screen here, but I'm replacing this integral with u v. So that's going to be 1/3 cosine of 2 theta e to the 3 theta minus the integral of v du. So like I did before, I'm going to take that constant, the 1/3 that's part of v, pull it out in front of the integral, and then here's the rest of v. When I put du there as well, I have another constant. I have this -2. I'm going to factor the 2 out. And since it's a -2, I'm actually going to just change that to addition right there. So I get plus 2/3 in this application. And then the rest of du is going to be sine of 2 theta d theta. So we've applied integration by parts twice. What we have happening right here is we've actually recreated the original integral. This line is equivalent to the original integral that I can scroll back up to here. The original integral had e to the 3 theta sine of 2 theta d theta. What we have in this line is we have e to the 3 theta sine of 2 theta d theta. This integral sitting right here is equivalent to the integral that we started with. This is a pretty special situation, but you will see this a decent amount when you're learning different techniques of integration, mainly integration by parts. I'm going to write out a new line that says straight across the original integral, which I just scrolled down from the top of the screen. We looked at it a minute ago. It was sine of 3 theta, or excuse me, e to the 3 theta times sine of 2 theta d theta. That has to equal this. So I'm going to write this out as 1/3 sine of 2 theta e to the 3 theta. I'm going to distribute this -2/3 into both of these pieces, right? So I'm basically writing this line out. I'm saying it's equivalent to what I started with, and at that same time, I'm going to distribute this in. So when I do -2/3 times +1/3, that'll give me -2/9, and then that term is a cosine of 2 theta e to the 3 theta. And then when I distribute -2/3 into +2/3, that should give me -4/9. And then I still have the integral of e to the 3 theta sine of 2 theta d theta. Now, if you think about this as one great big equation. What we want is we want to know what this equals. We have a situation created right now that we can actually solve for that original integral. This is one of those integrals sitting over here. I have minus 4/9 of them over here. Why don't I just add the 4/9 of those integrals that sit over here to the one that's already on the other side of this equation? And if I do 9/9, right, 1 plus 4/9, that'll take me to 13/9 of this integral. So I'm basically combining like terms. The like terms are just big and goofy looking. They're actually the integral, the original expression we were trying to develop an antiderivative for. And then on the other side, I'm just going to have these pieces that sat outside the integral, so I'm just copying these down. And if you want to know what the original integral equals, well, you don't have just the original integral equaling something yet. You have 13/9 the original integral equaling something. How would you solve that for the original integral? Well, you would just divide by 13/9 or multiply by the reciprocal, multiply by 9/13. So I'm going to claim that the original integral here is equal to exactly what I have here times the reciprocal of 13 over 9. So I'm going to multiply by 9/13. Same exact right-hand side of the equation is getting copied into this set of grouping symbols here. And the only other thing that I have to do before I wrap this up is I have to recognize that I'm claiming that this bottom line is supposed to be the antiderivative, the indefinite integral of this expression. And anytime you take an antiderivative, what you always need to account for is the constant of integration c. So that's a theta there. Sorry about that. Here's your antiderivative. It's a problem that we used integration by parts twice in order to find the antiderivative for. And we actually had to solve for the original integral. This is a cyclic application of integration by parts.